We're basically making numbers from these 8 digits here, but they are, they're chosen in a particular order. We're going to add the two 4-digit numbers and try to get a multiple of 6 or try to not get a multiple of 6, depending on whether you're Martha or Nadia. Now, if something is a multiple of 6, then it is a multiple of 2 and 3. So that brings two things in. It brings in the fact that the numbers are going to have to either both be even or both be odd. And we need the digit sum, the final number, to be a multiple of 3. Now, the first one is you can kind of see that basically if if Martha picks an even number as the last number, then Nadia is going to have to as well. So that's kind of one restriction. But Nadia can guarantee that. It's just so the harder bit is going to be whether Nadia can guarantee a multiple of 3. So a good shout at this point is to maybe just play this game and just Nadia just needs to ensure that she's picking maybe the same we call it parity. Either if it's even, she's going to pick an even one. If Martha's one is odd, she's going to pick an odd one. So that's how I'm going to kind of try and play the game to start with, because otherwise you can get in. I think you can get in trouble. So, all right, let's say that Martha picks 1, then Nadia is going to pick an odd number 7. Okay, keep it the same because then we can guarantee a multiple of 2. Then we'll go with 5. All right, then it has to be the other odd one 3. Then 2. Let's go with 6, and then 4, 8. Okay, so we see that Nadia can guarantee a multiple of 2 because they're both even here, and then we're going to add them up. See if we get a multiple of 3 just with this example. Now here the digit sum is 16, 18. It's going to be 27. So this is a multiple of 6. Okay, using this kind of restriction. Now, was that a fluke? Let's try another game. So maybe go with 8. It's the first one, started with an even number. This time go with 2. And then we'll try an odd number, 5. Again, let's go with 1. What about an even number here, 4? Then it's going to have to be 6 to keep the parity the same. And finally, 3 and 7. Okay, so again, we're going to guarantee a multiple of 2. Right, actually, the digit sum is very easy to find this time. It's just going to be 9. This is again a multiple of 6. So this kind of brings the idea in, like, is it always going to be a multiple of 3? How could we investigate that? Because otherwise it feels quite tough to, know who's going to win or not. That's the main, I think what you need like a little strategy when you're doing this question. Either you try and show that that Marta can guarantee somehow that it's not going to be a multiple of 6. Actually, this, to be fair, is how I first went about the problem. I started thinking about the digits themselves adding to multiple of 3, but that was not the right path because you don't have to have that when to get a multiple of 3 overall. It would guarantee it if it did work, I think. Um, but yeah, it's not really the way we're going. So the path we're actually now going down is I wonder if as long as Nadia uses his strategy and makes sure that the parities are the same, then maybe it's always a multiple of 3. So let's have a look at the numbers they picked in a bit more detail. So let's say that Martha picks A, B, C, D, and then we've got E, F, G, H. And these digits are representing numbers from 1 to 8. Okay, so we're going to add these together. Now, we can't really do that in this form, but what we can do is write it in powers of 10 form. So A, B, C, D is actually going to be 1,000 A plus 100 B plus 10 C plus D. And then we're going to be adding 1,000 E plus 100 F. By the way, I'm explaining this as if this is like, oh yeah, of course you do this. I don't think this is although when I first did this question, I did write it down because I remember, um, proving the divisibility by 3 or 9 rule. This is how you do it essentially. So I knew that, but to start with, I didn't kind of do this. I didn't think about how I could use this to investigate that it's necessarily a multiple of 3 from here. Kind of stopped and then went down another path. So that's going to give us right now. Actually, I'm gonna now use the same idea as when you do the divisibility by 3 proof. And if you haven't seen that, you're probably going to not know what to do here. So I would recommend looking into that. But actually, the way I'm going to do it now will give you some. Oh, sorry, will give you some insight into that. Actually, I'm going to kind of step away and let's do it. Just for a 3-digit number, A, B, C, let's prove that if this is divisible by 3, then the digit sum will be. So we can write it as 100A plus 10B plus C. So what you do in this case, let's say this is divisible by 3, then we can write it as 99A plus 9B plus A plus B plus C. So you see the digit sum coming in. So if this is divisible by 3, then we can see that 99A and 9B are both divisible by 3. So this has to as well. This must. And the same actually applies for 9. It's exactly the same argument. And if you extend it to more digits, it's the same idea. You're just going to get like 999A or whatever. So you can extend it to any number. So that's kind of like a little, just I wouldn't say that was a rigorous proof or anything, but just a little idea. But it's actually the same idea that we're going to now use here for when we're adding these together, because I can write them as 999. I'm actually going to factorize out. We've got A plus E here, and then it's going to be 99 B plus F plus 9 C plus G, and then I'm going to be left with A plus B plus C plus D plus E plus F plus B, C, D, E, F, G plus H. Now, the thing is, in this case, we know that these are going to equal 1 plus 2 all the way up to 8. Okay, because it's not just any old digits. We have to use 1 to 8. And we can quickly work this out by doing, I mean, you can add them up, or you can do a half times 8 plus 1. That's your triangle numbers formula worth being aware of. So we get 36. Of course, you can do it a long way if you want. I'm not going to explain that here, but I get 36. And so therefore, um, the answer must be divisible by 3, since each term is individually. This term is divisible by 3, this one is, and 36 is. So what we've actually shown is it doesn't really matter how they play out the game. We will always get a multiple of 3. And we can therefore solve the problem from here. So basically, the sum is necessarily a multiple of 3. And Nadia just needs to ensure that the parity, that is whether it's odd or even, the parity of the last digit is the same. And she can do this by choosing the same parity throughout. There's the same number of odd and even numbers. Okay, and that is actually it. I'm just going to demonstrate it with an example, e.g. 4. So pick 2, 7, pick 1, 5, pick 3. It doesn't matter what numbers we pick other than parity being the same, and then we're left with, say, 8 and 6. And this will give us 4, 9, 8, 6. Divisible by 2 and 3, so 6. And therefore, Nadia can always win. All right, really interesting question. Tough, I think, to do this kind of argument, but I hope it makes sense now. I did see in the solutions that they kind of accept like if you did lots of numbers and you like tried every single sort of example, if you're keeping the parity the same. Um, I don't know. To be honest, I can't quite get my head around that. I'm not going to talk about it. This is a much better general proof. We've actually proven that the answer will always be a multiple of 3. Really great. And then we've made an argument for how we can guarantee it's a multiple of 2, which means that Nadia can win. Okay, good effort. Good question.